The last little piece of what we have going on, I'm hoping that this is actually recording correctly, is we're going to be looking at even and odd functions. So this is kind of a new idea. So even and odd. Now, this is kind of an interesting name for something. It's calling a function even or odd. But if you kind of pay attention to how they look once we actually deal with the stories, you'll understand why they are named what they are named. So an even function. Now, right off the bat, notice it's called an even function. So that is already saying the thing is a function. You don't have to determine if it's a function. It has to be an even function. So starting there, the definition of a function is one in which, I'm just going to write it this way, super duper fast, f of negative x is the same as f of x. Now that's kind of a strange idea. Did you guys catch that? Which means, literally it means i.e., as in, for example, f of 2 is the same as f of negative 2. F of negative 8 is the same as f of 8. Meaning, if I plug in something on the left side of the axis and I plug in something on the right side of the axis, what happens? You get exactly the same result. So here's the deal. So check out my little function, let's call it g of x, because I want you to understand it doesn't have to be the letter f, it's any function at all. But let's imagine this guy right here. If you plugged in 2 and negative 2, would you get the same answer? 2 squared minus 6, negative 2 quantity squared minus 6. Are you going to get the same answer no matter what you do? But see, to prove it, what you're going to do, and this is what I need to see in your work that you're going to do today, is you write that, which means back from Algebra 2, remember how you did this little composite notation? This would say literally replace the x that you have with what? What should go in that hole? Negative x. Now, what is negative x times negative x? That's positive x squared, right? And so what happened is, notice this g of negative x became exactly where the problem began. See, that matches the definition of an even function. Fairly simple little idea. So this one was a good example of an even. Now, any guesses right now why that was an even function? It was an even exponent, wasn't it? Now, you might look at this 6 over here and say, but the 6 didn't have an even exponent. Yes, it did. That was technically, math speak, 6x to the 0, and 0 is an even number. It is an even number. Now, we can actually do some things that are a little bit weird, like you could do x squared minus 2 over, let's say, the absolute value of x. Now, that may feel a little awkward, but again, is this even? If I replace x with negative x, do I get exactly the same thing? Well, if I replace x with negative x, is this exactly the same as that? Now, that's kind of weird, but does the negative inside that absolute value do anything? In this case, it would not do anything. That is, again, another example of an even function. Now, as it turns out, visually, what's that going to look like then? If something is even, if 2 and negative 2 have the same answer, negative 8 and positive 8 have the same answer, it has what is called y-axis symmetry. In other words, isn't 2 on the right side of the y-axis and negative 2 is on the left side? And what am I saying is that they're the same. If you go over here, see how negative 8 and positive 8 have the same answer? That means when I make them as a mirror image, they look the same. So I kind of got myself a little bit ready to go with this thing right here, with a little Desmos thing. And so, see this top function. Now again, I hope, can you guys see that okay? Is the font too small? Do you guys think this is an even function? Like if I replaced x with, let's say, 3, I got -9. What do you guys think is going to happen if I put -3 in? Do you think I'm going to get the exact same answer? Do you see how that shows that they're in fact the same? In fact, if I scroll in, do you see the little symmetry right there? They perfectly match. Well, visually, as soon as I turn the graph on, boom, what do you see about the graph is if you could make a folding line right down the y-axis, what do you notice about them? They're perfectly identical. Now, you might think, well, like every year I have a lot of students really dislike this concept. See how 4 and -4 match? You can kind of go through that. But why, if you were ever asked to graph this thing, why would knowing that it is even be super duper helpful? You only have to plot one side because as soon as you know one side, what do you automatically get? The other side comes for free. Would that be pretty helpful when it comes to graphing? If you're going to plot a whole bunch of points, you know what it looks like. That's super duper helpful. So I have a couple other examples here that you can see. You tell me, what do you think? Is g going to be an even function? Would replacing x with -x give me the same result in function g right here? Now, what sets it up? Why would this work? Because what happens if you square or take to the 4th power a negative number? What's going to happen to that negative? It's going to go away and become positive. So do you think this one right here will in fact be even? Well, let's see. Now, this doesn't prove it, but I'm just going to make up a number. I'm going to try the number 4, and I got 13.85. So what do you think should happen if I plug in -4? I should get, now that doesn't prove, one example doesn't prove, but it does give you a pretty strong idea that it is in fact the same. Let's turn that on. Do you see the symmetry? It's perfectly symmetric. Now, if I did something even just a little teeny bit like this, now watch what happens. I'm just going to put an X right here. What just happened? See, look at the examples. 4 and -4 don't give the same answer, do they? Look at the symmetry. Do you see how it's broken? Now, why was this one not symmetric? Well, the -x to the 4th is going to be good, isn't it? This is going to be good. But what happens to the x right here with a 16x? If I replaced x with -x, wouldn't that become like -16x squared? I mean, -16x? It's not going to be exactly the same as where the problem started, okay? So the technical definition of how this works is a function is only considered even if, when you replace x with -x, you get the original back. This right here, guys, is the work you need to show me. So every single time you're going to do that. Now, I got to give you odd. Now, odd is a strange idea, and I know most people get even pretty easy, but odd is a little bit strange. It's a function if f of -x. Now, f of -x means you're going to replace all the x's with -x's, okay? But in an odd function, you actually don't get the original function back. You get the opposite of the original function. That's really super weird. Which means if I plugged in f of -8, it's the same thing as if I plugged in f of 8 with a negative in front of that. Is that kind of weird? That's kind of strange. Or f of +2 would be what? 2 would be the same as -2, but flipped over. Now that's a super duper weird idea. Now, as a hint, what did you notice about most of my exponents up here in this even chunk? They were even. Any guesses what's going to happen in my odd idea? What are the exponents going to be? They're probably going to be odd. So a perfect little example of that would be something as simple as 2x cubed minus 5x. Now, This is your proof. On the test, I would like you to know how to prove if something is in fact odd. You can look at this and what do you see about your exponents? They're odd. That should kind of lead you to a good place. But look what happens if I try g of negative x. Now, the rule says I rewrite the original function and what goes in both holes? I put in opposite x. So let's go through the process. What happens if you take negative x times negative x times negative x? You get negative x cubed, and I get positive 5x. Now look up here. Is that identical to where I started? That is not the original function, is it? Is it the opposite of the original function? Look critically. See, if I factored out a -1, I would be left with 2x cubed and a negative 5x. What is this thing right here? That's the original function. That is the opposite of g of x. So that makes it work. That actually totally works. This is what makes something an odd function. Now, in terms of the symmetry, that's a really, really strange symmetry that you're probably not used to. It's called origin. And origin symmetry is weird. I think y-axis makes sense when you fold something across a line. You guys have probably seen ink blot tests before, right? Those always have that kind of symmetry across a line. This is a strange symmetry because the origin isn't a line. What is it? It's a point. So what happens in origin symmetry, it actually has a 180-degree rotational symmetry. You can pull the graph around. So I have a couple of examples that I could show you right here. I'm going to go ahead and fix this one back and turn it off. Make this go away. All right. So see h right here? What did you notice that I did on purpose with all of my exponents? I made them odd. That was trying to be kind to you. So if I plugged in -2 and it says -42, you tell me what's going to happen as soon as I hit +2. It's going to be +42. If I hit -1, it says 0. What's going to happen when I hit +1? It's going to be the opposite of 0, which is still 0. No big deal. Well, look at this thing. Kind of a strange idea, but if you could imagine putting your finger right here at the origin and you spun it 180 degrees, what would happen? It would rotate all the way around. Now watch how this works. I'm going to see if I can make my computer do this. Watch what happens. What is h of -x? See, is it even? See, I replaced x with -x. Are they the same? No. Look, is the green and the black the same? No, they're not the same. It's not even. See, h of x and h of -x are not the same. But the question I have is h of -x the same thing as -h of x? See, this is the definition right here. I'm going to turn that one off. See this? That replaced x with -x. Are those two graphs, in fact, the same? So this thing right here, replacing x inside and putting a negative on the outside do the same thing. Do you guys see that kind of spinning symmetry that happens in this one? It's kind of a weird idea. So what that has is everything that was sitting in the first quadrant right here means it has a mirror image where? Down here in the third. Where is this guy right here going to show up that's in the second? Down here in the fourth. Hopefully you can kind of see it. That is a more subtle one. I'm going to go ahead and turn these things off. How about this guy right here? That's just now, I went ahead and I made it a teensy bit harder. I got x over x squared minus 4. What do you guys think? Is x over x squared minus 4 going to be even or odd? X over x squared minus 4. Now that may seem a little bit weird to you, but what happens if I replace x with -x? I think I called this thing k of x, but I'll fix that when I get there. What is k of -x? Is this over this. So what really messes with people's heads is in this case, I have a mixture of odd and even exponents, don't I? But what happened to the bottom? Look at it critically. What is negative x quantity squared? Isn't that x squared? What happened to the -4? Well, nothing happened to the -4, did it? But what's on top though still? A negative x. Well, check that out. This is the opposite of the original function, isn't it? See that negative? It's still there. So interestingly enough, you know what an odd divided by an even is? It's an odd. And if we go back and we look at our little picture right here, look what happens if I turn that thing on. Do you see the spinning symmetry that these things are the same if I sort of rotate them? I hope you can kind of see it. Now, in the work that you're going to do today, here's what I would like to see you do. What is j of negative x? See, now if I do j of negative x, so did I get the same graph? Is purple the same as blue? No, they're different. Huh. So it's not the same. That shows you it was not even. Replacing x with negative x didn't give me the same thing. It's definitely not even. But is j of negative x the same thing as the opposite of j of x? See, did that actually produce the same answer when I put the negative in the other place, in the outside instead of the inside? That's a proof or shows you that is in fact even. And so just for fun, I did one more right here. So what do you think that one is? Is that even, odd, or does it fit anything? What do you think? Anybody think it has y-axis symmetry? See this hump to the right? I should have a hump to the left, then I don't see that. Does it have spinning symmetry about the origin? Not really. Now here's the cool thing. To me, it's thematic about like politics right now, which I'm not going to get into politics. But is it easier to build something up or tear it down? Tear it down is way easy, isn't it? Like you can just make somebody look terrible. All you have to do is give an example, right? So this is a critical idea. This definition that I gave you right back here, I'm just about done with this idea, but the definition that I gave you right here says that for any x that I pick, this has to be true, and if it is, it's even, correct? So if I say x, how many examples am I giving you? This is really important. X is a variable, right? So if I say it's true here, what am I saying that is true is every single time for every case. Same thing right here for this definition. So what if I gave you one case where it failed? Would that make it fail? Because if the definition says it must be true, if I want to disprove something, would an example disprove? That is a subtlety that most people don't get. People think an example can prove. An example never proves, but an example can disprove. That's why in politics, you'll notice both candidates, what do they both do? They attack each other. They give examples of the other one's failure because if they try to say why they're good, it is very hard to prove that you're good because then you have to do it all the time. An example of somebody else's failure is super duper easy to get. So check out, all you would have to do to disprove it is, let's just pick up a number like 1. You see how it says 0.833? So what do you think is going to happen if I try -1? Did I get the same number? No. Did I get the opposite of that number? No. So what that means is it even? No, because they're not the same. Is it odd? No, they're not opposites. By the way, I love the fact that odd and opposite kind of go together. So what does that leave? It's not even, it's not odd. We just call it neither. It just doesn't have any symmetry, so I can't play symmetry games to make that thing happen. All right. And we've got a lot of examples that we could go to do that with. And so that is actually part of your assignment. That was part of the 1.2, I believe. B had a little bit of an idea about even and odd functions. And that's really as far as you're going to go today. So I'm going to give you guys a worksheet, which is I call 1.2C or 1.2 extension. And you're going to start playing with domain, and you're going to start playing with range. But what I'm also going to do is I'm going to give you access to Desmos Classroom. And I'm going to share something with you guys from Desmos Classroom. I'm kind of pulling that up. Can you see this all right here? I think so. I can't see. Yep, I'm logged in as me. That's good. And my custom, and it should be this one right here. So you guys are going to be this thing right here. You're going to log into that right there. So go to student.desmos.com, and if you type in that thing right there, you're going to work on a little worksheet packet, but then you're going to kind of back your work up in Desmos Classroom. So I'm asking you to do some work on paper, but then you're going to validate what you see when you actually do it in the classroom. I don't know if you guys have ever used Desmos Classroom, but we're going to do two different things today on Desmos Classroom. So did everybody get that written down okay? So let's just go ahead and get ourselves started. I thought maybe we could look at one of those together. Come on. Share screen, here we go. So what you're supposed to do is you're supposed to look at this, and it says, let's find the domain. Okay, so what are the two things we said we want to watch for in domain? What do you never want to do? Never divide by 0 and never take a square root of a negative. Well, guess what I don't see here? I don't see a square root, so I'm not worried about that. So I'm going to come in here, I'm going to factor this. That's x plus 3x minus 3. This should help me see something. So what are the bad guy values for me? What are the things that I can't have? Domain says do not be 3 and do not be negative 3. But I tried to hang something out there for you. See that plus 3? I'm hoping that that really jumps out at you. You see it? What did we go over yesterday? This is a brand new concept yesterday. What happened when we had a common factor top and bottom? That was a removable. So this one right here was a removable. So in the graph, what's going to happen when I try to do that is I won't even see it. Now, why won't I see this thing? Because it should be infinitely small, super tiny. How about this one? Is this one super tiny? No, this one is a infinite discontinuity. And you can be a little bit, you can abbreviate a little bit. You don't need to write out the whole word discontinuity. You could put DISC, and we're going to be fine. So hopefully that's going to be fairly straightforward. And in Desmos Classroom, I just asked you to actually take a look at the picture, validate what you see, and answer a tiny little bit more on it interacting. So that's the end of my lesson. We are good to go. So it's going to be work time for the next little while. And so I'm going to resume recording. And let's take a look at this thing right here. Okay, so I gave you guys a new little thing that I kind of mixed emotions about doing this to you, but there we go. What we're going to do today is I do need you to also put in this code right here. So you have two Desmos activities, and this one is actually extraordinarily light. It's KNX XTZ. You could type that in. You should therefore have access to it. It's honestly a really simple little thing. But what I did for you guys in that little activity, I'll leave it up for another 2 or 3 seconds, and then I'm going to take that down because I want to show you what it is. But in here, there are a total of 12 things that I would like you to know. And that probably seems kind of silly, but I'll show you what I mean by that. I'm going to hit it in preview mode so I can show you kind of how it looks. But in preview mode, this is me looking at it. See, this graph right here is the identity function. And so if I start playing with it, are all of these just modifications of that blue line? So I picture it like somebody handed me a line, and then I had silly putty, and I started pulling and stretching on it. And I could lift it up and move it down, but ultimately all of these are just modifications of that original, what we call parent function, which is just x. Anybody have a guess what would come after x? My next function is x squared. And I could start pulling on this one, and I could start, see, I can make it, see, this is ax squared plus bx plus c, and I could start moving it around. And I could see how it kind of behaves, and how, as we move it all, every parabola is that blue parabola just been pulled around. And in fact, if I make a negative, it goes over. That's fine. I took my silly putty and I turned it over. No big deal. But it's all the blue parabola moved. What would come after x squared? There you go. And then you can look at the cubing function, and we can start playing with the cubing function. We can change the values of a, b, and c, and d, and we could change how that cubing function looks. We can move it around. So in assignment 1.3a, which is the other part, so tonight's homework is 1.2c, the worksheet, and 1.3a, which is a textbook assignment, but you can use these little things to help you do it. It's a little visual thing. Actually, 1.3a is very simple, almost like 1.1, where you're kind of matching a lot of things together. But this can help you do it. And so you're going to notice if you go back to this thing, there's a total of 12 screens in it because there are 12 functions. So there's x, x squared, x cubed, the square root function, and it kind of just cruises along with all the different versions. You guys ever seen these before? Sine and cosine function. This one is the one I talked to you about, the greatest integer function. It's the one that's like when they charge you for a cell phone bill or a parking garage. This is the weirdest one we'll talk about later. I don't really know. We almost never use it. It's called the logistic growth function. But 1.3a, the list is in there. You're going to be able to do this. You don't really have to submit anything with this. You're just going to use this to play around to see how the functions look when you're doing your homework. So if you're looking at a cosine function, you could click on this and play with it because I have it set up for you to be ready to go. So anyway, that's kind of the rest of the homework. So you guys have about 5 minutes. Try to get a little teeny bit more done. Please make sure you got both of those codes down. So this code was K and X, XTZ. You do not need to submit anything on this. This was just supposed to be a helper tool for you. And I think everybody has the other one, so I'm not worried about it. So we got 5 minutes left. Do you need it again? Okay. Wait. The first one. Oh, okay. Let me go back then. It should be this one right here. And you guys are working at HCP X6H. Yes.